the underlying process of this, in fact, can be described by this Markov decision process. So the Markov decision process is really a framework, that a mathematical framework, try to model the decision making, that when you have when you actually try to model a sequential decision making, in fact, and you would be able to say, depending on this Markov properties, and say based on the current state, and you can take action. So let's looking at this, what we mean by Markov properties. They have a various of that kind of dependency, independency. So for example, in the transition, is that if you know the current state, you don't really need to know the previous states, that the future state would completely depend on the current state. And also the policy itself is that when you actually have this policy is stationary. When I say stationary, it's independent of time. And if as long as I know the state, then my action would depend on that. So really is that the state itself, the current state, would capture all relevant information from the history. So that's why we call it Markov decision process. So formally, it's that it consists of a set of states, right? That the system transits from jumping from different state to state, depend on the action you take. And then you have a set of actions, and then you have this transition property as we defined. This SA is equal to S prime given S and a given current state action, the transition to next state. And also gamma here is the discount factor, really to discount the future reward as we've seen in the repeated game. And also we have this reward function, is that you have this given current state action you're taking, and you would receive reward. And also in some, it really depends on the application. Some counts that you see this, that this reward also depends on the future action. Sorry, also depend on the future state that you transition to. Even in some cases, that state only depend on, the reward only depend on the current state. So with that, then you would have, can specify the dynamics. I think about this, that you can have a given current state, and the agent taking action, and the system provide the reward, and then transition to, the system transition to next state, and then this agent taking action, and the system give the reward, and transition to next state, and so on and so forth. And then you can, in fact, collecting the cumulative reward discount by this gamma, factor, and this become your cumulative reward. The goal of this, that for the agent is try to taking this action, right, in such a way to maximize this cumulative reward. Think about this, that this action would have the opportunity to alter the environment, isn't it? Because this transition, right? Because this transition, and then because this action, they would reach to the different state, and that in different state, right? In the simplest case, and you will receive different reward, and maybe also depend on your action to receive different rewards. Therefore, this action, this policy, the policy would have influence on where the system would transition to, and therefore have the influence also on this reward, cumulative reward. Therefore, the goal is to find out this optimal pi in such a way to maximize cumulative reward. So this is what I try to say. It's here that's why you value function of given state would depend on the initial state, but also depend on the pi itself. So the nice thing about this is, in fact, if you try to trace back these the origin of reinforcement learning. And you can actually trace back to the field called control theory. And actually, one of the subtopics is called optimal control. And also this particular, this widely used algorithm called, dynamic programming. And the central part of the dynamic programming is the essence of math, the fundamental math behind this dynamic programming is Bellman equation. Okay, so let's say what Bellman equation is. So now we given this pi, okay, or given this pi. Think about this. Once you give this pi, this transition is, the probability of transition would be fixed, right? Would be stationary. Think about this, right? Once you have this state, then I'm gonna write in just for the case of deterministic case, right? Given that, think about the system gonna move stochastically if the transition is stochastically, right? And become Markov process, right? And then suppose I have reached to this stationary sort of a probability in terms of, how frequent you will reach to a certain state. And then based on that, and because each state you would able to receive, given each state, you were able to receive certain reward. So if you're doing it sequentially, you can in fact write it down this value, right, which is expected value function, which is expected, which is expected cumulative reward that taking into account stochasticity, maybe from here, the policy itself or the transition itself. So stochasticity, taking into account stochasticity, condition on your initial state, right? And that initial state is S, and condition on that the pi. Later we show that in fact this probably is irrelevant if you are in this a certain if you fulfill certain condition that you sort of don't really care too much about where you started. Eventually will converge to stationary distribution of this of the state visitation frequency. So you can write it down this expected reward, expected cumulative reward given current state, which is equal to the state that you're going to receive. Sorry, the reward, immediate reward you're going to receive at current state. The decay, right? The time decay is counted by the time decay, and the future reward. This is the future reward you're going to receive. The future reward would depend on two things. That one is that given the current policy, which kind of state X prime you're going to reach to, right? And also given that I'm going to reach to my next state X prime, what would be my accumulated reward in that case? Okay, so this provides a very interesting, a very useful definition of the value function, because this value function would also depend on themselves, right? Think about this. And then we can actually be solved that, we can make use of this and to, find a way to solve it. So dynamic programming is a provide a principal way to solve it, in an iterative way to solve that, solve this. So you could also have this so-called optimal value function. Is that given this pi, suppose we know this pi, and because of that we can devise the value function. Okay, then the optimization, the reinforcement learning task becomes simple. Is that we just try to figure out this policy in such a way can maximize this value function. Okay, this value function. Then I will reach to my optimal value function, right? And if you according to this Bellman equation or Bellman optimality equation, And you can actually write it down, decompose that this optimal value function into your immediate reward and also reward that you're going to receive in the future. Bear in mind, the difference of this is that Bellman equation is that when you're given a pie, right, you have this relationship of like you can able to decompose that value function with immediate reward and future reward. Same thing here, but the only difference is that this optimality condition is that you need to maximize this future reward, okay, based on that expected, cumulative reward you estimated, right? Then you need to figure out the action so that would give you maximum future reward, because the current reward is already realized, right? There's nothing you can optimize with, but the future reward you do, because you know this transition, and therefore you would able to do that. So just to emphasize that the discussion we discuss about this update, right? This sort of a value function update. We assume that we know the environment. In other words, we know this transition, right? When we know this, or this formula even given us, when we know that, what can we do? How can we find this solution? So think about this, that if you know this transition, right? And then you can using this to calculate this optimal value function. Once you have this optimal function, it's quite natural, it's quite straightforward, you can actually get optimal policy. And you can actually prove that for every state and action, right, state or every policy, that this optimal one would always guarantee you, which gives you the largest value. So, so how can we do that? We do by iteration. Okay, suppose we know this transition, right? Suppose we also know this reward function. What you can do, think about this, is you could renderize this, right? You can renderize this. Suppose you have some kind of representation of this V function. Let's say if the state is discrete, then this value function is nothing but a table, right? But a table. And for each of the table, you can basically say this is state, and then the value of it is basically the value of the V, right? V state, let's say state 1, state 2. Sorry, so that's, I'm just trying to write down here. So state 1, state 2, blah, blah, blah. And then you enumerate all possible states you would count. And given that state, what is the value, right? What value you got, and so on and so forth. So essentially, this is a table. And you could initially renderize this, right? And then you could do this update because you know this, right? And you also know the reward. Therefore, you're able to update that. Once you got this updated, right? You could go back to figure out the policy to realize, sorry, not realize, but try to improve your policy, because it's V changed, therefore policy change. Policy change, you can get a new sort of a value function. You could do the update, or you don't really need to update. You only update at the end, but you can update this iteratively. Once you have this new updated table, and you go back to here again and do the update. Depending on whether you're gonna, make use of the policy, then you have two different algorithms. One is called value iteration, that only rely on you do, value function update, or you have this policy iteration, you update your policies each of the time. But in either way, it's an iterated update. So this is a pseudocode for value iteration. And I said that you have the discrete sort of state space, and also you have discrete sort of action space. Then because here the assumption is that you know the transition, right? You know the transition. and also you know the reward function. Suppose you know this too. Therefore, you could say, given any state, you will get this value, right? Given this any state action, you would basically know what the next state would be. If you know this too, and then input is a randomized value function, okay? A table, let's say you're not necessary to be random, it could be like a sign everything 0. And then you can actually update that, right? Is that for each state, you do the calculation and do it again until it converges. So just to give you an example, let's say you got this maze as we explained, but here is a simple one. You just have this goal as your goal state. You initialize V1 as 0, and each time we do the value updates, you can find that the value changed, and the one close to, the one close to goal state would have a higher reward. Can you maybe one question? Can you maybe let me know why, given this value update, why they would able eventually learn a correct value function? Because if you're looking at this one is quite far away from this goal state, then they would have a lower sort of a value, but the one close to it, they would have a higher value. Any reason why you were able to achieve that by value iteration? So the signal, the signal, where the signal comes from is actually from here, right? From here. Because think about it, is that when you try to update, I'll have a good example later, but just to intuitively to make sure that you understand that. So each time you do the update, you're looking at the future, you receive your, these rewards you get in the current state. But in this case, it's really like a one step, whether that would reach to the goal state or not. But of course, in the case like here, then you would have a chance to reach to that goal state, right? And therefore, when you do that, you would have a, not minus, but higher reward that you given here. And because of that, you would have opportunity to have that observation. And this future one is basically say the neighborhood have a chance to transition into those things, right? Therefore, can make you some of the reward there to, eventually reach to update yours and eventually propagate back to the whole state. Therefore, if you do this update, although the signal is relatively weak, but it turned out in this simple example, only 7 steps that you would, almost get, you would already become stable. So this is the value iteration, but you can obviously do for policy iteration. So the policy iteration is that each time you sign this, right, given that policy, in this case, would be, again, the policy would be just table as I indicate, right? And then you could have this based on that to calculate the value function. And once the value function received, you can base on this value function and to figure out the optimal strategy that you come with. And then once you have that, you can go back to define that, update your value function. And so you can see the crucial step here is that each time you need to update your value function. And then you've done job. So one question though is that here is that you not explicitly mentioned the policy, but eventually you want to get a policy, isn't it? So how can you do that? So in fact, it's just trivial. Is in the sense once you have this value function, the relationship with this policy is this, right? You can just at the last calculation is that given this V, you get this policy, and that's it. You get that optimal policy. So this can be illustrated by this diagram is that you started with Vn pi, that's a random Vn pi. And the policy iteration is that you go here to given this pi, and to update this value, make sure that this value represents the evaluation, okay, represent evaluation of the policy. In other words, I can say, if I follow this pi, what would be my expected reward gonna receive? So you have accurate assessment of this policy. And then once you got that, you do this gradient update to update your policy again. And then iteratively, you converge to the optimal ones. So you could obviously have a random policy as well, isn't it? So here is the update using policy iteration. Is that you're starting with a random policy. You can see that after a few steps that give you a good solution already. So this is sort of a comparison with this policy iteration and value iteration. So value iteration is a greedy update strategy, right? And in policy iteration, this value function updated by Bellman equation is in fact relatively costly. But you can do that sort of a calculation by own to see why is that. So they have the problem comp. It depends on the situation. Sometimes value iteration works, sometimes policy iteration better. So one of these questions, people would ask is that, okay, now given I have this value iteration, okay, policy iteration, would that be always converge to the optimal solution? Would that solution would be unique? How far the algorithm would be, when we come to the conversion? So this all can be solved by, looking at the contraction mapping theorem. Remember that when we're talking about Nash equilibrium, we also turn that problem into contraction mapping, and then eventually prove that, indeed in that case, if you not they're given that kind of definition of Nash, particularly in the mixed strategy. If you are my best, I'm your best response, you are my best response, and we create some kind of, we didn't call mapping, right? Oh, sorry, we didn't call a function mapping. Right? It's a correspondent mapping because the output of that is a set rather than a value. So it's still in that case that with this contraction mapping, we've shown that there's a fixed point, and because there's a fixed point, we basically prove the existence of this Nash equilibrium. So here we still need to using the similar mathematical tools for now allow us to do the analysis. So here, so instead of doing the set kind of mapping correspondent, we do in the function space. Think about this. Given the state, right? You count a value, and this in fact the function can be think about a vector. Can be think about vector in the high dimensional space. Let's say you have a limited number of states. You have a finite number of states. In this case, you have a state 1, state 2, state 3. Think about that. If you write it as a table, you have, as I said, right, you have this V S1, V S2, V S3. The value of that is a value of that function, okay? So this basically is a three-dimensional vector, and therefore can be represented as a point, in this three-dimensional space. Think about that. Each value function would be in the, in this case, in the three-dimensional vector space, it would be the one point in that space. So then think about this, that the function is a vector, okay? And then the Bellman backup, think about the Bellman backup can be considered as, when I say Bellman backup, right? I mean this. I mean either this, okay, or this backup of value function. This backup is doing a certain operation on this point, okay, on this point. And what the effect of it is basically move this point in this space. Okay, suppose you have an optimal value function here. The backup function would guarantee you to move, gradually to the optimal ones. Okay, then you think about this I shouldn't call it backup Bellman backup function, but rather Bellman backup operators. So think about these operators. The operators is the matrix over this, high dimensional vector and transitioning to a different position, different point. So in the Bellman backup, there's a nice property of that. I will show that eventually they will, converge to that optimal point. So that need to have certain measurement about how close, my value function here, another value function here. So how close this value function is, let's say pi1, pi2. And we here using this called infinity room to measure that. So infinity room can be, it's just nothing but kind of maximal. You have a distance between them. And then I pick up, I basically enumerated all possible states. Just look at the distance between them, pick up the highest. That is my, using it as a distance measure. And then, as I said, that these operators, this Bellman backup function is nothing but kind of operator over this value function, or a point in the high dimensional space. And we will show that this operator is gamma contraction. In other words, when I say gamma contraction, is respect to the measurement that we measure, the distance measurement, like the maximum norm that I measure. And this, either Bellman optimality operator or either Bellman optimal operator or Bellman operator, they would have that kind of property. So in other words, that if I apply a Bellman update once, okay, I have two value function. If I apply one, the distance between them would be smaller than I just looking at the distance of the original value function. Let's say we have two pair of value functions. And the difference between them, I will guarantee which is smaller than this, the factor factorized by this gamma parameter. Okay. So let's finish off this, and then we will have a break. So this Bellman expectation operator is basically defined like this: is that you have given the policy pi, okay, given the policy pi, and as I said, with the Bellman equation update, you given the existing immediate reward and this is future reward that you can able to calculate. They are stochastic, right? Because this, as I said, this uncertainty from the transition, uncertainty from the policy itself, and so on and so forth. But it does able to sort of say, given this Q function that I got now, and this is sort of a formal way to write this operator over the function. Think about this: is the T, this Bellman expectation operator is on a function, so that's why it's over Q, okay, regardless of what state it is. And then we'll transform it into the new, okay, new Q function. This new Q function would be, equal to this, the update that you got for all of the state action pair that you consider. Sorry, we haven't talked about the Q function yet. So Q function is that when you have the state function, this is only depend on state, but you can also write it down as, state and action function is to specify for my current action, what kind of action that I'm gonna take, and that would leading to the final expected reward. And sometimes you find that's easy to operate to do over this Q function rather than value function. Think about this, that the Q would have a notion of the action, therefore indicate the value of the action given certain state. So, so you could apply this Bellman operator on this Q function, as we said, and then the same thing is that when you have this optimal pi, then would be the optimal Q function. It's just notation, yes, and then given this Q, right, you can actually to directly obtain this the policy, right, condition on that. If I want to follow this Q value function, what would be my action? Basically, this is going to tell you that what would be your policy. And so this contraction mapping, suppose we know it is contraction mapping, right? Suppose we know it is contraction, or we will pull that later. If it's a contraction mapping, let's say fulfill this condition, right? Then you could actually say, suppose, okay, this Q2, sorry. So if you follow this, and then you could basically say each time when you do this Bellman up backup, you can find the distance between these two are become smaller, right? Each time when you do the update backup, this could be, these Bellman optimal backup operator, or this Bellman expectation sort of a backup operator. So in either case, if they follow this, right, a contraction mapping, this gamma contraction, if it's have this property, then we'll see that each time they will shrink, And if one of them is optimal, okay, you can see that actually will become closer to the optimal ones, right? So if it's one of them is optimal ones, let's say Q2 is optimal ones. And you can basically say, if this is optimal ones, any update to it gonna be themselves, right? Any update to it gonna be themselves. So here, this guy wouldn't change at all. And the other guy changed, then you can basically say, eventually they will converge to that. So, but what we need is we need to prove this operator have this contraction mapping property. Okay, how can we prove that? It's actually quite straightforward. So you just measure that given this Q1, Q2, right? You do this contraction mapping. You do this operator applied to it. Then you take distance between them, right? And you can really write it down by using Bellman equation. And because it's a subtraction, so the reward is immediate reward is the same. Therefore, it can be removed. And for this, okay, I basically, so here is the absolute value here, right? I'll take this absolute value into here. And because of this operation, and this, the one that absolute value is outside this summation, you can see it will always smaller or equal than, if I take this, absolute value within this summation, okay. And also is that if I take out this maximization over this summation or over S, in other words, I'm going to choosing this, the one at the highest value of it. And this one is obviously, this one become constant. When I, after this, taking out this state, I have no state whatsoever. And this one has a state, and therefore summation is 1, right? And then basically reach to that equality. And then you take this maximum over here, then you got this, gamma contraction condition holds. Okay, so once you hold that, and from this fixed point theorem, so last time we talked about fixed point theorem, it was on this correspondence sort of mapping, right? But in this case, it is not. It's more on this functional mapping. So then once you do that, you can actually show, the fixed point exists, and this for value update, right? If you use one of these optimal, you can eventually they will converge to these the optimal ones. So to illustrate, is that you got this nice property. Then you basically say one of them is optimal ones. Then you say you guarantee always converge to that. So this is for this Bellman optimality backup function, but you can also claim for the expectation backup function. You got a similar proof here, so I'm not gonna spend it. You can have a look. It's quite straightforward to get that. So by this contraction mapping theorem, then they will basically show that the value iteration will converge to the optimal value function. And however, the problem though is that in this tabular case, when I say tabular case, is that you're able to represent the value function or even the policy, as a table. Okay, but in practice, when you have a neural network, when this decision space of this action and also this state space is much large, it's very large, then you probably is infeasible to using this table to represent that, and you need to have certain functional representation, right? For example, you can use a neural network. Then it's very difficult to actually prove the convergence. Okay, and so I think it's actually still an active research area, really to understand the properties, some of the proof, even convergence proof of the presentation, when you using this neural network to represent the value function, represent Q function, or represent the policy itself, and what sort of proof, convergence proof that you would have. So I think it's a very active area. If you're interested in that, certainly you really worth pursuing that.